Now our discussion will be from drift velocity of free electrons, the relaxation time, electric current, and resistance. Before starting with the text, you will understand that these all things like drift velocity, electrons, free electrons, electric current, and resistances, they are all related to the metal conductor. The metal conductor is normally in the form of a cylinder, and we find that all atoms of this metal conductor are arranged in three-dimensional repeated pattern, and free electrons are randomly moving. So when we apply the field, then only electrons will begin from negative to positive, otherwise they will be in random motion. So now we start with the main context, that is metals contains a very large number of free electrons. Normally their order is about 10 to the power 22 in 1 gram material, and they behave like gas molecules. These electrons move at random with a velocity of about 10 to the power 5 meters per second in the vacant space between the stationary positive ions and collide with these ions. The average time taken between the two successive collisions is called relaxation time. It is represented by tau, and its value is 10 to the power minus 14 seconds. When potential difference is applied between the ends of the conductor, it provides a small velocity to the electrons towards higher potential end along the length of the wire, which is superposed on the random motion of the electrons. This constant small velocity is called the drift velocity. The electron velocity is generally represented by Vd, and its value is found to be of the order of 10 to the power minus 4 seconds. If potential difference between the ends of wire of length L is V, then intensity of electric field that can be given as E is equal to V over L. The force exerted on each electron is given by function F is equal to EE, and E can be replaced by V over L. Therefore, we find that force can be estimated by function E into V over L. The acceleration of electron due to this electron is given by F over m, or it is EV over ml. That is, for force we have computed force, that is EE over m, where m is the mass of electron, which is very small, nearly 9.1, 10 to the power minus 31 kilograms. The drift velocity is the velocity required. The drift velocity is the velocity acquired by electrons in a direction opposite to the applied electric field due to acceleration of electron during the relaxation time tau. Hence, drift velocity is acceleration into time. Therefore, drift velocity is acceleration multiplied by relaxation time, and similarly, drift velocity can be replaced by E over m multiplied by tau. So, EV over ml into tau. If cross section of wire is A, the number of free electrons in its unit volume is N, and the drift velocity of the electrons is Vd, then electric current flowing through the wire will be I is equal to NEAVD, where A is the area of cross section, N number of electrons, conduction electrons, Vd is drift velocity. We can write this number as I is equal to NEA, and for drift velocity we will substitute the value of drift velocity, which is found to be EE over m multiplied tau. And if we calculate the whole number, we will find that I will be equal to NE square tau over m into A over L into voltage V. If the resistance of the wire is taken as R, then according to Ohm's law, R will be equal to V over I. And for voltage and current, we can put the numbers. Voltage will remain as it is, and for current, we can compute the value, that is NE square tau over m multiplied A by L into V. So the net function will become R is equal to m over n squared tau into L over A. If the mean free path of electron is lambda and root mean square speed, RMS speed of electron is Vrms, then tau is equal to lambda over V RMS, and resistance, which is taken as voltage over current, we can put the value of tau in the equation and we get ml V over n square lambda A. This V will be RMS speed. Resistivity of conductor is indicated by rho, and rho is RA over L. For this, we put the value of R here. So value of R is taken as ml V over n square lambda A, and the net function of rho will become m over n square tau, and conductivity of conductor, that is reciprocal of resistivity, that is conductivity sigma is equal to 1 over rho, which is found to be n square tau over m. On bending the wire on several places, its resistance does not change because the resistance of wire depends upon the free electron density and the relaxation time, which do not change on bending. The number density of conduction electrons in copper is 8.5 into 10 to the power 28 per meter cube, and the mean free time is tau between the collisions in 2.5 into 10 to the power minus 14 seconds. In this case, we have to estimate the conductivity of the copper wire. So this is one of the application of conductivity. We have got, the number density of conduction electrons is given to us, and mean free time is 2.5 10 to the power minus 14 second. We have to estimate conductivity, and the formula for conductivity, as it is clear, n is square tau over m. We substitute all the values given to us. Mass will be given as mass of electron 9 into 10 to the power minus 31 kilograms, and the remaining values are constant. So we find that the conductivity of that wire will become 6 into 10 to the power 7 mho per meter or Siemens per meter. You will further remember that mho means we are referring to conductance. So it is conductance per meter. Mho is a unit of conductance, and conductance is reciprocal of resistance. So basically, when we use conductivity, it is conductance per unit length or Siemens per meter.